converges to 0 almost surely. And so these suggest, right, so we're not actually saying we reached the minimum, but under some other assumptions, we can see that we get actually the desired solution. What we're going to focus on in this talk is this assumption of being IID. So in a lot of applications, this maybe isn't very realistic. And so what we wanted to do was just to relax this assumption just a little bit. And so as the name suggested, and we've seen before, we're going to relax the IID assumption to a Markovian assumption. And I think this is realistic in a lot of applications, which I'll show at the end, where we're either doing sampling from a large network, where maybe sampling IID and having to move around the network and at far distances is challenging, whereas a Markovian trace around the network is easier. In real data that's coming in, like weather data, video data, and things like this, I think a Markov chain is much more realistic than being independent. So what we were able to prove, this is with Laura, Haine, and myself, is if we have, instead of being an IID data sequence, we have an irreducible Markov chain on a finite state space and unique station distribution pi, then we get kind of similar results. So the following holds. We again have the same convergence of the empirical loss and the surrogate loss, which suggests that this replacement that we made is reasonable. We also get that error goes to 0 almost surely. And we also get that the gradient goes to 0 as well. So this was our main theoretical contribution, which gets the same results, but again, replaces this IID assumption with a Markov chain assumption. So the actual proof looks different. There were some non-trivial things in there, and I think it relaxes this assumption to something a bit more practical. Okay, so I assume I haven't been interrupted, so there's no questions yet on this.
There's one question, and perhaps this is a good moment to ask a short question. Laszlo asks, he's wondering how this method can be used for noise reduction, similarly to how people use PCA for that purpose.
Yes, so I do have a slide on this, which maybe I can talk about when I get there. So we did do an example of denoising with video.
Okay.
And so you can imagine you would do this the same way. So the hope is that you either learn the dictionary items without noise and you can use them to reconstruct, or even we see that we actually learn the noisy dictionary items as well. Yeah.
Great. Maybe if I can ask a short question for clarification on this theorem that you're presenting. The previous result by Julian Merald and collaborators holds also in the redundant dictionary case. And I believe your setting is that of a low rank matrix decomposition. So the number of columns is lower than the dimension of the data. So what I'm asking is, this result that you just presented, does it hold also in the redundant case?
Yes.
Great.
Yes.
Thank you.
Yeah, so it's the same setting as theirs.
Great.
We also have a question from Renee in the chat asking what are the applications with the irreducible Markov chain assumptions that where the irreducible Markov chain assumptions hold. Like,
yes, so I will show some of those next. That's what's coming. Besides the ones that I will show, I mean, just if you have, so there's two settings. One is where we're actually sampling ourselves. So if we're in video or imaging where we're sampling patches, and we have the ability, or a network, we have a large network, we have the ability to walk around the network and sample local patches, and that's definitely Markovian, right? So if I were to sample a network ID, I'd have to be able to move very far around the network, and that's impractical for really large networks. For images, for images, we can sample according to some Markov chain, and you'll see that we do that here as well. For real data, I think, okay, so one can argue whether or not real data is Markovian, but if you don't believe it's Markovian, you definitely don't believe it's independent. So for example, we've applied this to COVID data, to weather data, where it's more believable that, the next day's case count or temperature is reflective of the previous days versus completely independent. So I think even in the real settings, this is closer to the truth. Yeah, great questions.
Thank you, Deanna.
Okay. Okay, so I went a little fast, so I can kind of take my time through here. So I'll show some of these are kind of real, and some of these are maybe more fun, just to see like what we can do. So this is kind of an example I've alluded to here. So we're doing network dictionary learning. So this network is built from the book Adventures of Huckleberry Finn by Mark Twain. So we just do, we create a word adjacency matrix. So these are the words and whether they're adjacent to each other in the text or not. And so we've also done this for other large networks where it actually is challenging to traverse the network, but I don't have that example here. But this one's kind of interesting because I guess Huckleberry Finn, the way it's written, there's like a lot of structure to the text. And so this is what the original word adjacency matrix looks like here in the center. And over here are the dictionary patches that we learned from a Glober chain sampling. And so this is an example of a Markov chain. It's used actually in many physics applications. And so my postdoc Haine did a lot of experiments also with some icing models and other things motivated from physics. But it was interesting that it actually worked pretty well here as well. So we learned these kind of 3x3 dictionary patches. Here's some examples of what they look like. And then on the right here is the reconstruction of the network from those patches. So it suggests that those patches do kind of capture the structure of the network. And so the idea would be, I mean, obviously for text, this is kind of maybe not as interesting, but here the structures are very simple. The text might be easier to understand, whereas if you did it with a different book, then hopefully you could look at the different features and might tell you something about the author. In fact, there's lots of interesting work in my department about learning features about authors just based on punctuation and things like this, and you can actually predict whether two authors are the same or not, just based on the network structure of punctuation, adjacency words, and things like this. So the dictionary items could actually be used potentially to do some of this type of identification. But for now, this is just kind of a fun example. This is for images. So here we're kind of showcasing that one can use these dictionary features for image compression. So here on the upper left, this is the original image. I'm actually not sure how you say this person's name. This was my student's favorite artist. And here we've learned 100 dictionary atoms. This is 25 of them. So we're using patches again, and we're sampling the patches using some Markov chain. And on the bottom here, we have done again a reconstruction using this dictionary of 100 20 by 20 color patches using ONMF. And so there are some parameters one can choose. So we did 1,000 randomly selected sample patches, random according to some Markov chain, and with various overlaps and so on. But again, these features aren't just random noise, right? They're kind of interesting to look at, and they're definitely enough to rebuild the image in a fairly nice way. This is one that we were kind of interested in, and I think it would be nice to pursue this further. So we were looking at whether we can use this ONMF idea to do color restoration for images. So this was just kind of our test case. So we took a fairly simple, so we used ONMF again on I think 1,000 patches, and we learned these color. color patches here, the color information. So we discarded all of the color information, but then used the colored patches that we had previously learned to try to reconstruct the image. And although it's a little bit blurry, you see that the color actually was reconstructed accurately. And so this, I think, suggests something interesting that, of course, the question is, can we transfer this knowledge? So can we use trained dictionaries and other colored images to reconstruct and restore color in different images? So this was the same image. The question is, can we do this on other ones as well? I think that would be interesting future work. Here is some basic candle kind of moving around. On the left here, so this top, so these are 4 frames from this candle video. And this first dictionary consists of, this is 4 features learned from kind of classic NMF. And so not using any history across time in the video. And on the bottom here is some dictionary features using ONMF. And kind of the takeaway we got from this was, as you would expect, ONMF should do better because it's using the history versus a single frame at a time. And so we were able to kind of pick up more interesting features from the image. Like this is actually the flame here. This is kind of like the background, the wick and things like this, versus kind of the same repetitive static images. On the right, we have kind of a similar experiment. This is the same video, and we're going across time now as we move down. And the left is the actual candle video frames. And then the remaining 4 are those frames corresponding to particular elements. So you see how they change with time.
We have a question in the chat. Arik asked, it looks like reconstruction go to low resolution. What are the parameters to tune to obtain high resolutions there?
Yeah, like especially in these examples. So patch size is definitely one, and then the number of atoms that you learn. So it's kind of like the compressed sensing setting in the sense that if you learn enough features, then obviously you have all the features you need. You have every single patch in the image. And then you would get a high resolution. But learning larger patches and fewer of them leads to higher compression. So there's always that trade-off. So this is, I think, it looks like low resolution because we've done these large patches and a small number of them.
Where does the patches show up in the formulation of the non-negative factorization?
So the patches are the columns of W. So you can imagine vectorizing the patches, and those will be the columns of W. So the patches here are the features that we learn. And then the number of those is R. That's the number of columns in W. Yeah, so there's definitely a trade-off in terms of the reconstruction error will, of course, be smaller as R grows. However, I should say that even if you take R to be the full dimension, you're not ever guaranteed to get exact reconstruction, right? Because you have the non-negativity constraint. And so here there was a balance between wanting, I mean, typically the goal isn't always to have exact reconstruction. The goal is to learn something from those features, right? Because these features are interpretable. So you wouldn't be using ONMF if your goal is just reconstruction. You'd be doing PCA or something else. But if your goal is to also use these features to interpret something about the image, then you would want ONMF. Okay, so here's the denoising one that I promised was coming. So we just took, again, this candle video and added noise, just Gaussian white noise to it. And you can see here that we were able, so on the bottom, here are the dictionary atoms and across time. And so you can see, so this bar up here kind of shows the coding matrix And so you see that we're able to actually separate kind of the flame itself from the noise. So there is hope that, that this could be used for denoising. So this is, I would say, very preliminary, and I'm not suggesting that this is like the best one can do, but I think that there is, as somebody asked, some hope that these type of methods can be used for this. Okay, so more recently, some things we've been doing involve prediction. So how do we use ONMF as a prediction tool? So the idea here is, so we're going to talk about, for example, COVID data because that's readily available. So we have data that is confirmed cases across time, number of deaths across time, a number of recovered patients across time. And so the idea here is we're going to kind of imagine that you have this time series. I'm going to draw this horizontally with my hand. And what we're going to do is kind of imagine, instead of having patches, we're going to have a sliding window across time, and we're going to learn these dictionary atoms. So we're going to view this as a Markov chain and use ONMF to learn the dictionary atoms across time. And hopefully that's going to pick up local patterns and local behaviors. This is, again, an example where I think assuming that this data is IID is very unrealistic. Assuming it's Markovian, maybe a little bit closer to the truth. And so what we're going to do is we're going to learn these dictionary atoms, and then to do prediction, we're going to look at time t today and fit the dictionary to the next, say, 6 days. And that next 6 days that we go beyond today will be the prediction. So that's how we're going to use this. So that will hopefully use these local patterns to enable us to project outward. So we're using the dictionary atoms from the history that we have to fit the future. And so this is what we're doing here. So what this shows is dictionary atoms. This is over a 6-day period of, again, these daily cases in 6 countries. So we used Korea, China, the US, Italy, Germany, and France. This gave us kind of a good mixture of patterns and trends. And so each dictionary atom is 6 by 6 by 3. So we have 6 days, 6 countries, and then 3 time series. And so we are kind of showing these patterns, and then we show the numbers below our metric that we use to show how relevant each thing was. So if we just glance through here, and sorry, the legend here is on the right. Unsurprisingly, China is often looking different than the rest. That's unsurprising, since at this period in time, China was doing something much different than other places. And the US is often kind of more, I don't have an exact example here, is usually a little bit steeper than some of these other ones. So we've looked through this, and there's some interesting trends here. But the interesting thing is, how can we use these dictionary atoms to then make predictions? And so this is what we were able to do. So here's, again, some example of these dictionary atoms, which are giving these local patterns, local features. And here's our prediction. So this is for Korea. So blue is the actual true data, and this red is the prediction that we've made. And so we're graphing them over top of each other, but this red is what we would be predicting given only previous history. And so we do a surprisingly very good job at prediction. And this was the time that we stopped. We had no history. That was what we predicted. So what I'm interested in here is, I think this is maybe not as good of a tool for things like COVID, but for like financial data where these local patterns really do have strong implications. I think this is actually going to be a very powerful tool. And what I would like to do is to do things like COVID prediction would be to incorporate a model. So using like an SIR model and then learning parameters as our dictionary atoms and then doing some predictions there is something that's ongoing. Okay, so this was for confirmed cases, this is for deaths. kind of similar here. This data is a little bit more reliable, but we see kind of similar abilities to make predictions. This is for recovered cases. We start seeing these jagged lines, unfortunately, because, so this happens when you see these large spikes in the data. So when the real data has large spikes, those large spikes kind of take over when you make predictions. Okay, still okay. So I will end with something we've done very recently, and we've extended this ONMF approach to the tensor world as well. So going beyond matrices, doing things with tensors, and the transition is sort of natural. So here is an example of what one can do with ONTF. So it takes a little bit of work to extend the algorithms, and I'm not going to talk about in this talk. I just wanted to show one of the results for what one can do when you take it to tensors. So here we have a color image, which now instead of treating as one single matrix, we're actually going to view it as a tensor where the third component is the color. So we have a slice for each channel. And again, we're learning these patches. So these are our dictionary items for each of the 3 dimensions. And over here are the reconstructions that we get. So again, as somebody already mentioned, you get kind of this like lower resolution reconstruction, but it seems to be working fairly well for doing what we're doing. And possibly these dictionary features could be of interest. Here we definitely see like kind of some geometry happening in this first slice, and then possibly some other textures and things happening. So I think it's interesting to take this to tensors as well and do things with video and so on. So it has the ability to be extended, is kind of the point of this. Another example that one can do with tensors. So here we had some examples of the cortex of the mouse, a mouse brain over time. So it's a video sequence. And they're really interested in looking at different activations. And so using this video and applying ONTF, we can learn all sorts of different spatial activations. These are the dictionary features. And then the coding matrices kind of tell you when those things are being activated. So this is a kind of a nice way to be able to quantitatively see when different areas of the brain are being activated automatically rather than having to do it by hand. So I think that's an interesting direction to take this. We also apply this to weather data. Maybe I won't spend too much on this, but if you have many different cities and you have weather data over time, that turns itself into a tensor. And again, you can learn different patterns. So here you see kind of an obvious daily pattern. You see weekly patterns and so on. And you can use these to just learn different features about different cities, or you can also learn them and use them for prediction as well. So I think I'll end there, and thank you everyone for your attention, and we have time for questions.
Okay, thank you so much, Deanna. Maybe in the interest of time, we'll ask the attendees who have questions to join us later for the Q&A with Deanna. And now we will move on to the next talk in the afternoon. Thank you so much, Deanna.
Thank you.
All right, thank you. Can you hear me?
Yes.
So our last seed update for the day is from Professor Tom Haine from the Earth and Planetary Sciences Department at Hopkins. While we don't have time to get into his turbulent past, suffice it to say that he is leading some of the most exciting projects in oceanography in the IDIES community. Given the critical role that oceans play in regulating climate, I guess we're all lucky that Tom's specialty is the North Atlantic. Perhaps even more awesome than his research, at least for me, is the fact that he is a ultra marathoner. I guess these are people who get to the end of a marathon and say, "What? That's it?" Anyway, without further ado, here's the amazing Tom Haine.
Thank you, Annie. Let me share my screen. Can you see it full screen?
Yes.
Okay, so I'd like to talk about towards the development of scale-dependent, non-local, turbulent closures in rotating stratified flows. I'm grateful for the opportunity to speak to you. I'm grateful for the seed funding from IDIES, and I'm very grateful for the support of my co-authors. Charles Meneveau and I wrote the proposal, and Miguel Jimenez Arias is a postdoc who's working with me, Marathon Planetary Sciences, who's done almost all the work in what I'm going to show you today. So let me try and unpack this title for you by starting with a discussion of ocean circulation. So the rotating stratified fluid dynamics piece is ocean circulation. I'm interested in the ocean circulation, and the central picture you see here is a Landsat image. So it's a satellite image of a patch in the Baltic Sea. And if you look up here to the left, you can see the scale of this image. It's maybe 50 or 100 kilometers on a side. And the image shows the color of the surface of the ocean. And that reveals the concentration of chlorophyll in the water. And this image was taken a few years ago in spring or in summer. Every year in the Baltic, it looks like this. And this is a phytoplankton bloom, cyanobacteria. So it's a microscopic blue-green algae. And of course, it's spectacularly beautiful, and you see the vast range of scales present in the ocean circulation. And if we zoom in to this particular feature here, then you can see there's just this incredible detail. So now we're at a scale of a few kilometers, maybe 10 kilometers on a side. These streaks here, they're characteristic. You see them everywhere if you look closely. And you can now actually see individual ships and some aircraft contrails and so on. So when we look at a picture like this, we think about the processes that control the distribution of the plankton and the surface of the ocean. And there are ocean currents, non-tidal ocean currents, operating at a vast range of space and time scales. So at the largest scales, you can see coherent eddies. For example, here there's one that looks like a dipole. These are called mesoscale eddies. Characteristic scale would be maybe tens of kilometers across. They'd live for several weeks, a few weeks or several weeks. And then these mesoscale eddies are stretching and folding and stirring the phytoplankton into these filaments. And then at the smallest scales, at least in these images, these sort of feathery-like patterns, they're probably due to Langmuir circulation, which is an interaction between the wind and the surface wave field. So we have a vast range of scales in the fluid dynamics. And of course, almost all of this is unresolved in, for example, climate models. So on the left, I show some Minecraft type images of the typical resolution for the Intergovernmental Panel on Climate Change climate models. So the one that's been published and analyzed recently in the last few years is called AR5. It's about 80 kilometers on a grid cell. And so everything I'm showing you here in the Landsat image is maybe one or two of these blocks. AR6, which is being computed right now, maybe halves that resolution. Now you can start to see some of these islands appearing in the Baltic. But almost everything you see in this image is below the resolved scales. And so one of the things that we're interested in is trying to understand the effects on the large scales of the processes that are unresolved in the climate models. So in broad scale, that's motivating our projects. Now there are a zoo of processes that are going on in the Baltic in this particular day, many more than we can individually address. So we have to pick a single process and study that in some detail. And that's what I'm going to transition to now. And that process is ubiquitous. It was certainly going on in the image that you just looked at. It's called shear dispersion. So now I'm going to switch to a more technical part of the talk and tell you about what we hope to do in the seed fund project and what's been achieved so far. So shear dispersion is an effect. It's the dispersion, the spreading of a passive contaminant, like a plankton, for example, a tracer, in a current which has got, for example, shear. So it's got a different direction in this particular case as you go across this channel. So here you can see the velocity profile. And if you imagine laying down a patch of dye and then letting it evolve over time, so here's the initial patch of dye, then it will spread to the right at the bottom and the top of the channel, and it will spread to the left in the middle. And then this would be the channel average distribution of that tracer. Okay, so this is resolved, where you have the cross-stream direction resolved. This is averaged across the channel. Now, shear dispersion is the enhanced spreading of this tracer along the channel due to the alternating current. Okay, so it's the enhanced longitudinal effective diffusivity due to current shear. And it was originally discussed by G.I. Taylor in the 50s, and then most recently, the images here that you see here are from a nice paper by Ali Mani and Park last year. So we want to parameterize or account for the effect of this shear dispersion. In other words, we want to be able to describe what's going on average across the channel without having to resolve the details of this alternating current. Okay, so these figures here show some approaches. DNS, it's direct numerical simulation. So you start from an isolated tracer patch. Now going up the page is time, it spreads, and it is diluted as time goes by. Taylor came up with asymptotic theories for how that spreads. So there are two versions here, leading order Taylor and higher order Taylor. And at least in long times, they're reasonably accurate. And I'm going to come back to that. And then the thing that caught our attention in this Mani and Park paper is this MFM-based method. So MFM stands for macroscopic forcing method. And it's a numerical method that allows them to recover the closure operator that represents the channel averaged effect of this spreading. Okay, so if we're going to build a climate model that can't resolve the details of this cross-channel current shear, we need to have a closure operator which will account for the averaged effects of that shear dispersion. And this MFM method is a numerical method, seems to do that quite accurately because these two are the same, although they're not identical. The other thing I should say before I move on is that the Taylor theories are not very good at short times. And in particular, they are biased so that they exaggerate the rate of spreading at short times. And then if you look, for example, at this one, it kind of has a square root type behavior, these contours, whereas the DNS has a linear behavior. Okay, well, the square root behavior is a bit like diffusive spreading. That's what you'd expect if it was just a diffusive spreading. And the linear contours here is what you'd expect if it was being advected. Okay, so the DNS is suggesting that there is a combination of effective advection and effective diffusion going on. Okay, so Miguel has worked on this problem as we were getting started on the seed fund. His idea was that he was going to analyze this problem in some detail and then use that to understand the MFM method and then apply the MFM method to some other canonical circulation, fluid dynamic ocean circulation type processes. But we had a change in path because something interesting and serendipitous occurred. Okay, so let me tell you a little bit more detail about the way the problem is set up. So the microscopic, in other words, the fully resolved problem, is the advection diffusion equation. So theta is the concentration of the tracer. U0 is the peak of the current speed here. And for our particular example, it's got this cosine shape. So the average flow along the channel is 0. Okay, so the average of the cosine is 0. And then it spreads with an explicit molecular diffusivity, which is given by kappa. And we have periodic boundary conditions and no slip boundary conditions on the sidewalls. And we're going to imagine initially that we've got a cosine distribution of tracer, and then we're going to let that evolve in time. So this is a particular example. I'll move that out of the way, of K0 is a half. And now you can see the animation. So this is what happens when you let that run forward in time. The tracer spreads out and then eventually disappears. Okay, well, there's no movement of the average, the center of mass of the tracer, because there's zero net flow in either direction along the channel. And because it has this cosine initial condition, there's no, with negative tracer values, there's zero average tracer. So the long-term solution is just zero tracer everywhere. Okay, and so now here's another example, but with a higher wave number. So you can see in the middle of the channel, the tracer gets advected to the left, top and bottom, it gets advected to the right, and then it decays. So this looks more like advection and then decaying. Okay, so that's the kind of behavior. Now we want to integrate across the channel and average that behavior and figure out how to represent that. Okay, so here's the equation for the macroscopic or the averaged problem. So theta bar is now the average tracer equation, and it's averaged across the channel in this way. Okay, I'm going to come back to that. It's not the only way you could do it. It's the way that we've done it so far. And if you average the equation, then the first term is straightforward, the final term is straightforward, but you get this closure term here. So you've got d by dx of the average of cos of y times theta. Okay, so everything comes down to representing this closure term. And I've already talked about the picture on the right. These are pictures of theta bar, I mentioned that. Okay, so what Miguel has done is discover an exact solution to this problem. So he has found an analytic exact solution for theta, okay, for the microscopic advection diffusion equation. That's not been known before. And once you've got an exact solution for theta, then you can compute these other things, like you can compute the cross-channel average tracer theta bar, you can compute this averaged advection term, and then you can also infer the closure operator. Okay, so the closure operator is gamma. So this term here, the advection term averaged, I'm going to rewrite as gamma operating on theta bar. Okay, so it's equal to this by definition. So once you have an exact solution for theta, you can compute all of these things, and that's a great advantage. So let me tell you a little bit about what that looks like, and then where we're going to go next. So the new exact operator is scale dependent, it's non-local, and it's linear. So let me tell you a little bit about how it looks, and then I've got a few more slides with some technical details in. For small wave numbers, the closure operator looks like this. Well, Taylor had d2 by dx squared. Okay, you've got a prefactor which is saying that the dispersion is enhanced, but it's still diffusive. Okay, well, we have a correction which is biharmonic. For large K, in other words, for small scales, the closure operator looks like it's advective. Okay, so that's different, qualitatively different. And for intermediate scales, it looks something like this, like a square root derivative operator, or this form here. And so that's non-local. So those are interesting things, and I can quantify this in a moment. Okay, so here's what we want to do moving forward. We didn't realize that we were going to get this exact result. So we're going to use it to calibrate the approximate numerical methods, like the MFM method. We're going to use it to check approximate analytical methods, and we're going to use it to try and understand the physics of the shear dispersion. Now, this is one specific case of this zoo of fluid dynamical processes, and it's for one specific example of cross-channel filter and a particular shear profile. Both of these, I think that we can relax. I think there's good prospects that we can make these generic and still have an exact analytic solution. And then what we hope to do is to extend this method, or at least the improved calibrated MFM type approximate methods to other canonical closure problems. Okay, so let me just say one more technical thing before I finish and maybe take some questions. In this closure operator, everything comes down to an eigenvalue, which is this omega here, omega sub 2n. You get an expansion in terms of Matthew functions, which is very interesting. I'd never heard of Matthew functions. And I'm showing you the first two, n equals 0 and n equals 1 eigenvalues. And so this is the real part, and this is the imaginary part. Okay, it's plotted against K0, the scale. So Taylor was down here. Okay, he had n equals 0, which is the low frequency limit for small scales. And this is well fitted, as you can see, by K squared, which means it's diffusive. So you get enhanced diffusion, but it's diffusive. Okay, way over here for large K, you've now got the eigenvalues split into complex conjugate pairs, and they scale like K or IK. That means it's advective. Okay, so at long times and small scales, it's diffusive. That's Taylor's limit. At long times and small scales, it's advective. And then the advantage of having an exact analytic solution is that you see all of this structure in between. Okay, so there is no simple closed form real space operator that can represent all of this splitting of the eigenvalue. But this is the exact analytic closure operator to this particular problem. So I think that's very exciting. And I will stop there.
Thank you very much. Any questions? I think we have time for a couple. So one question I had is, I mean, in the big picture, are you seeing anything in your models or analysis that keeps you up at night with respect to the impact on climate?
Both Miguel and I are kept up at night by being excited. I mean, Miguel figured it all out. So it turns out that you have to use Matthew functions. I've never heard of those before. A particular type of Matthew function, which is really quite new, and software to computer solutions to Matthew functions has only been developed quite recently. So that's why I think this would not have been possible. It would not have been possible in Taylor's day, but it would not have been possible probably even 10 years ago. But to answer your question maybe more specifically, if I go back to here, the working hypothesis of climate modelers, the people who do this stuff, on which we base all our climate projections, is that the intricate details that you see here doesn't make much difference to, for example, the 2100 projection of global mean temperature. So I think that's a good hypothesis. I mean, it's talking about scale separation between the very small scale, high frequency motions and the global scale, low frequency effects of climate change. I mean, I'm comfortable with that, but that is nevertheless a hypothesis.
All right, thank you. If there are no further questions, I believe I'm supposed to hand it back to Renee for the MINDS Thesis Award. Thanks again, Tom. Is Renee available? There we go.
Jeremias is going to do the introduction.
Yes, I'll take it from here. Thank you both. By the way, I presented Deanna before, but I realized that I didn't introduce myself. For those who don't know me, my name is Jeremiah Sulam, and I am an assistant professor in biomedical engineering department here at Johns Hopkins. And I'm also the chair of the MINDS Awards Committee. MINDS established the Doctoral Dissertation Award program to recognize and encourage superior research work in the foundations of data science by doctoral candidates across all of the university, across all of Johns Hopkins. This year, we consider candidates who have successfully defended their doctorate degree between September of 2019, last year, and August of the current year. And so today is really a pleasure for me to announce and present this year's Minds Dissertation Award to Dr. Chenxi Liu, who's here joining us today. Chenxi received his bachelor's originally from Tsinghua University before doing his master's in statistics at UCLA, and later coming to the computer science department at Hopkins for his PhD, where he was advised by Professor Alan Ewell. Through his PhD years, he also interned at Facebook AI, at Google Research, Adobe Research, and he is now a research scientist at Waymo. Chenxi's PhD receives this year's award for his dissertation on the automation and diagnosis of visual intelligence. In his work, as you will soon hear, Chenxi carefully dissects different steps in the visual intelligence pipeline. His profuse works carefully study different aspects of the automation of machine learning and computer vision systems. He pioneered work on efficient neural architectural search, both in supervised and unsupervised settings, to work in language level understanding of 2D and 3D scenes, further to the development of benchmarks for evaluating what can be referred to as a visual Turing test. To quote some of the references of Chenxi's thesis, his work is characterized by a genuine, deep, and rigorous understanding, seeking for novel and fundamental topics in machine visual intelligence. For all these reasons, the committee has decided to award Chenxi with the Best Doctorate Dissertation Award of this year, and it is truly a pleasure for me to welcome him today to give us a glimpse of his dissertation work. So welcome, Chenxi.
Thank you very much, Gerald, for the very kind introduction. I will now try to share my slides. Can you guys see?
Yes, perfect.
Perfect. Thank you very much. And hello, everyone. It is just my great pleasure to receive the Minds Doctoral Dissertation Award and to briefly present my dissertation at this symposium. The title of my talk and dissertation is on the automation and diagnosis of visual intelligence. And let's dive right in. So what do I mean by the phrase visual intelligence? Well, because of the word visual, an obvious ingredient in the visual intelligence pipeline would be the 2D images. In order for machines to be called intelligent, they have to at least understand the semantic categories present in the image. But is category level understanding the finish line of visual intelligence? Of course not. There are a lot more underlying interactions going on in an image, typically expressed in the form of natural language. For example, a boy is feeding the giraffe on the right summarizes the image much better than simply person and giraffe. And now going in the other direction, the 2D images are not the starting point of the pipeline either. We should not forget about the fact that they are the results of rendering and projecting the 3D scenes and objects. This figure now summarizes the complete visual intelligence pipeline considered in my dissertation. So what have I spent the last 5 years doing and how they situate within this pipeline? So my dissertation consists of 3 parts. I will talk about them all, but place more emphasis on part 1 due to time constraint. Part 1 of the dissertation is about automating structured learning for 2D recognition. So this concerns the critical recognition error within this pipeline, which bridges vision with language and converts signals to symbols. So we're now in the deep learning era. And when we talk about learning, we pretty much always mean weight learning. We have a nice automatic procedure, backpropagation, to learn these synaptic weights, which turns out to be extremely successful. But is weight learning the only form of learning? If we go down history lane a little bit, there's no doubt that these synaptic weights were inspired by real synapses in the human brain. But adjusting the synaptic strength is not the only form of learning exhibited by human brains. Our brains go through drastic connectivity changes within one's lifetime and also evolves in structure over generations. And these structural changes allow the learning of the synaptic weights to be easy and effective. Now, having spent some time on the human brain side, we see a blank space on the artificial neural network side. So part one of my dissertation tries to answer, can we develop the automatic procedure for the structured learning aspects of deep learning, which has long been overlooked? So this structured learning problem in deep learning is now more commonly known as neural architecture search, or NAS. Around summer 2017, this technology already achieved great success. And as illustrated in this figure, the black dots are the frontier achieved by human design models, and the red ones are those found by reinforcement learning, which already represented a better trade-off between accuracy and model capacity. But at the same time, these methods also exhibit clear limitations. They tend to be costly in terms of the computation power. Thousands of GPU days are required. So this is not only environmentally unfriendly, but also prevents this technology from being widely deployed. Therefore, when I started working on this problem in 2017, my first effort was to create the speed axis, trying to make NAS faster. By now, you're probably confused why NAS is so costly. And the reason is that there are exponentially many neural architectures to try out. And each trial would require training a network from scratch, which takes hours individually. We may have a manageable number of primitive building blocks at the beginning, but once we start allowing them to combine with each other to form novel architectures, the number of candidates starts to explode. In my work titled Progressive NAS, I essentially introduced a mechanism to aggressively reduce the number of candidates whenever the explosion is about to happen. Of course, this reduction is not done blindly. I introduced a predictor which is trained on the data collected and efficiently estimates the quality of an unseen architecture with only forward pass and no gradient descent. By iteratively carrying out these steps, the search terminates after trying out about 1,000 architectures, a sizable reduction from previous methods, as we will see very soon. For those of you who are familiar with the terms, the algorithm may be known as sequential model-based optimization, or a form of A-star search. In this figure, we compare our algorithm against random search and reinforcement learning. The first observation is that progressive NAS results come in 5 groups, and they correspond to the increasing complexity of an architecture. At the beginning, our validation accuracies are lower than the other methods because they have 1/5 the representation power. But signals accumulate as we progress. And when we reach the final stage, we found a cell with close to 92% accuracy with a little over 1,000 models sampled. And in order to reach the same accuracy, the RL method needs to sample 6,000 models. Therefore, we conclude our method is 5 times more efficient on this search space. And each experiment is repeated 5 times, reflected in the error bar for all curves. So we then evaluate the found architecture on the ImageNet classification benchmark. So the first group are the best human design networks, and the second group are machine design ones. We see that progressive NASNet 5 achieves 82.9% classification accuracy, which was the highest on the leaderboard around the same network complexity. So to summarize, we were able to significantly cut down the computation cost with 0 sacrifice and even slight improvement in terms of search quality. So after this work was published, it was quite reassuring to see that many papers joined in this direction of making NAS more efficient, and more breakthroughs were made. But I noticed that the tasks being considered were very limited. Essentially, only image classification was studied. Therefore, in my 2018 effort, I decided to create a new dimension, that is to include dense prediction problems as well. So modern convolutional neural nets usually follow a 2-level hierarchy, where the outer network level controls the spatial resolution changes, and the inner cell level governs the specific layer-wise computations. But the NAS papers at the time only automatically search the inner cell level while hand designing the outer level. So this limited search space may be acceptable for classification, but becomes problematic for dense visual prediction, which exhibits more variations at the outer level. As examples, here were 3 popular dense prediction architectures designed by human experts, DPLAB v3, conv, deconv, and stacked hourglass. And it will be a pity if these designs aren't even included in the search space. So capturing their core design principles, my work AutoDeepLab proposed the first search space for the outer network level. At the beginning, there are 2 downsampling layers that are not part of the search, but the gray arrows and the blue nodes represents different possibilities of spatial resolution changes. The goal of network level architecture search is then equivalent to finding a good path in this L layer trellis. This search space is general enough to cover many popular designs, including the 3 examples we just saw. Then how do we perform search within this search space? In this work, I used a differentiable formulation where I would associate a scalar beta with each gray arrow in the picture. Specifically, this means a tensor at layer L+1 is going to be the sum of 3 cell computations, each modulated by the respective beta value. And these scalars beta can be conveniently optimized with gradient descent, just like how you optimize the synaptic weights. And after these beta values are optimized, some connections will be strengthened and some will get weaker. The architecture that we will select is going to be the path with the greatest beta value product from left to right. And we decode this path with the greatest beta value product by running the classic Viterbi algorithm, which is very efficient and very fitting in this setup. So how does this architecture perform on benchmark datasets? Here we show its performance on cityscapes. Without ImageNet pre-training or coarse annotations, AutoDeepLab significantly outperforms the previous AVR by 8.6%. And with only coarse annotation, AutoDeepLab achieves a performance which matches the human-designed DeepLab v3+, even with ImageNet pre-training. And these 2 comparisons clearly demonstrate the effectiveness of using NAS to design semantic segmentation networks instead of relying on human labor and expert knowledge. So again, after this work was published, it was reassuring to see that many papers joined the direction of applying NAS on more diverse tasks. But I noticed that essentially all the research was conducted under the same supervised setup. Therefore, in my 2019 effort, I once again created a new dimension, this time studying the unsupervised version of neural architecture search. It's clear by now that the computer vision community has come up with a ton of different neural architectures over the years. They may be designed by humans or searched by machines, but what all these architectures have in common is that when they were originally designed, it was a supervised task that they were optimizing for. In this work, we basically traveled to a parallel universe where there was no semantic labels when deep learning came about. What neural architectures will we find, and will they look similar to what we have already, and will they work as well? To answer these questions, we conducted 2 sets of experiments. In sample-based experiments across multiple tasks, datasets, and search spaces, we discovered the phenomenon that the architecture rankings produced with and without labels are highly correlated. And in search-based experiments, again, across multiple tasks and datasets, we show that the architecture search without labels are highly competitive, not only relative to their supervised counterpart, but also in terms of absolute performance. And overall, these 2 findings collectively indicate that labels are actually not necessary for neural architecture search, which is perhaps surprising. And I'm excited to see how the field would respond. So we have finally got past part 1 of my dissertation. Part 2 is about diagnosing language level understanding. This part corresponds to the highlighted region in the visual intelligence pipeline. So diagnosis is necessary because we want to make sure AI is advancing in the right direction. Diagnosis is extra necessary for language level understanding because of the highly compositional and complex nature of language and reasoning. We want to make sure that the predictions are right for the right reasons instead of being cheap imitations. And I've done several efforts along this line through designing interpretable models that generate intermediate outputs and or building diagnostic data sets and or opting for a symbolic representation in the form of a graph. Part 3 of my dissertation is about diagnosing 2D recognition with 3D objects. And again, the corresponding region is highlighted in red. So sometimes we want to understand the weaknesses in our trained 2D recognition models. For example, do they work equally well for all colors? Do they work equally well for all viewing angles? I argue that diagnosis is better performed in 3D than 2D due to the clear physical meanings and the better disentanglement of object properties. And this part of the dissertation focuses on how 3D environments can bring extra benefits to the evaluation of 2D recognition models. Again, unfortunately, due to time constraint, I cannot expand too much, but please check out my dissertation or reach out to me if you are interested. And to close, I want to thank the many people who collectively helped me build up my dissertation. I thank my advisor, Alan Yule, and my committee members, Greg and Fei Fei. I also thank my GBO committee members, course instructors, awesome collaborators, and fellowship support from industry. Finally, thank you, JHE, for the great education I've received, and thank you, Minds, for the recognition of my dissertation. I will continue to strive for excellence in my next roles. Thank you for listening.
Thank you so much, Chenxi, and we look forward to seeing what those roads ahead will bring to you. Renee, over to you.
Let me see if I could share. I hope Alex is also there.
Yeah.
So all I wanted to say is that it's been a great pleasure to host the symposium jointly between Minds and IDEAS. I think it has been a great opportunity for 2 different communities within data science to get together and look at cross-fertilization of ideas. So I wanted to thank everybody for attending, all of our speakers for the great presentations, the same thing for the posters and breakout sessions. But I think I also wanted to take a moment to really thank the real giants behind being able to do and organize this event. It's the first time we have to do an event online, and I think we wouldn't have been able to do it without the great support of faculty as well as staff members who dedicated a lot of their time to the organization. So I wanted to thank Megan, Tara, Emily, and Caroline for taking care of all the logistics and making sure that the sessions were running online. And I'm sure they recruited a lot of help and didn't sleep for a couple of nights trying to get this together. So thank you very much. And also to Soledad and Jordan, who helped us put together the program, contacted the speakers and invited them and made sure that we had a great program together. So with that, let me pass it maybe to Alex, if he has some final words.
Yeah, so I also just can't do anything else and really repeat how good the symposium was. And of course, this was unfortunately not a substitute for the face-to-face meeting. And I think, but I would like to thank again to everyone, Megan, Tara, Emily, Caroline, Soledad, Jordan, to actually make the whole Zoom environment actually lively and active and interactive. But I also hope that maybe next year we don't have to do this in a virtual space, but we can actually rely on mixing personal interactions. Because in many of these meetings, much of the interaction is happening in the coffee breaks. And we also during the year, as we are hopefully transiting towards more opening up, we would like to do, I think, more of these mixers and shared seminars. So I think we will be actually, so we will try consciously post each other's seminars so that to involve the broader communities that we have now opened up. And hopefully also as the AI initiative is also slowly starting to happen at Hopkins, I think there will be tremendous opportunities for further collaboration. And I'm really glad that we actually did this together. Thank you very much. So.
Great. So I think the last part of this meeting will be still the QA session for Deanna, but since that happens in a separate breakout session, we wanted to have this opportunity to close the meeting here. And so I guess in 3 or 4 minutes, we'll see you in the other link. Maybe Jeremias or Caroline, if you have the link, you can copy in the chat for others to attend.
So once again, I would like to thank everyone for attending, and I hope you had such a good time as Renee and I did. Thank you very much.
Perfect. So there is the link, and those of you who are interested in Deanna's talk, please join us there. See you soon. Bye-bye.
Bye-bye.